Welcome back. We're going to be going through potential energy today. This is assuming that you already understand conceptually how potential energy and other energies work and transfer back and forth. Now let's actually go and figure out what potential energy is. How do we calculate it? Let's get into it. So first, potential energy is the energy due to the position, not the motion. Instead, motion is kinetic energy. And it's symbolized by the capital letter U most commonly. Sometimes it'll be PE in different textbooks. Obviously, that's really confusing because it looks like it's two variables multiplied by each other. So most of the time, people actually use a capital U for potential energy and then subscripts for different types of potential energy. A system of objects is said to have a certain amount of potential energy because of the arrangement of the objects, again, where they are, the position. Consider, for example, some sort of rock that's held 4 meters above the ground. Because the rock and the earth are separated, if the rock is released, the objects will attract one another. And they attract one another even if they're not released. The rock could apply a force on an object while it falls, thereby doing work on the object that it's pushing on, maybe. If the rock was only 2 meters above the ground, it would fall less far, and therefore it would do less work. The higher the rock is placed, the further it could fall, and the more work it could do. Therefore, the amount of potential energy on the system depends on its position there. Now, the rock example, you can kind of imagine the rock, getting faster and faster and faster, as we've done in the simulation before. But we also use this exact idea with water, right? Hydroelectric power and hydroelectric dams. How does that work? Well, we have a big dam that's built up, a huge concrete wall. You can think of like the Hoover Dam or something like that. And you have water below and water up high, and you go, wait, this water that's at the top there, that has this, it's really high up, and therefore it has a huge distance that it could fall. Let me go and draw the displacement vector for that water that's on the top there, and it could fall all the way down and then come out. And if we routed it just right, we could have it go through like a little turbine there and make it turn and push on some turbine, and therefore do some work on some turbine, which then creates this electrical energy. And we'll talk more about that in the next unit there. Okay, cool. So that's how we use potential energy to actually make other things happen, or one way anyways. Okay, potential energy is another kind of energy. It's like kinetic energy. To change the amount of potential energy in a system, remember the transfer of energy, has to be done in the system. Therefore, when when work is done on a system, it might change the system's kinetic energy, potential energy, or some combination of both of them. This modifies the work kinetic energy theorem, turning it into the work energy theorem, saying that, hey, if I add up all the work, it's going to be, changing the kinetic energy, or I could also think about it as changing the potential energy, or some combination of both of them. All right. We want to have a way to keep track of how much work an object could do because of where it is. To do this, we need to choose a location to call the position of zero potential energy. If a rock is on the ground, can it fall and do work? Well, generally we'd say no, so we usually call the ground the position of a minimum, or really zero potential energy. Now, is that really true? Well, you could think about that and go, oh, if I place something that's on the ground there, that thing doesn't have anywhere to fall, but then think, oh, wait, could I make it fall? What if I took that ground and I got a big shovel? Could I make it fall? I could dig a big pit in the ground there. And now could it fall? Yeah, it could. Well, if I call that zero, then, isn't that zero? Well, if I put that rock now in the pit there, now will it be a zero gravitational potential energy? Well, no, I could just dig a deeper hole, and so on and so forth. So without going into a huge explanation of that, we are simply choosing where we're going to call our zero gravitational potential energy, and oftentimes it's one of two locations. Either one, it's on the ground, like here in this case, or number two, it's the lowest position of the problem that you're looking at, or the scenario that you're looking at. Usually the lowest position of the scenario you're looking at usually simplifies things more often than not. So usually that's the best one, but both are, common ones. And you could really you could choose this gravitational potential energy to be 0 anywhere that you want, and things will work out. If you chose it here as 0, and then the rock did actually fall into here, well, now what happens to its gravitational potential energy as it falls in? Well, that goes down. But if it started at 0, then the gravitational potential energy at the end would be a negative amount. Yeah, that's actually true. And most people, though, don't like dealing with the negative gravitational potential energy. And so that's why a lot of times people will use 0 at the lowest point, so then they don't have to use these negative values, which is a little bit conceptually hard to think about, but still accurate. Okay, moving on. To figure out how much potential energy the system will have with the rock at a certain position, the potential energy at the end, the F for a final there, we need to figure out how much work it took to move it from where it had 0 gravitational potential energy on the ground, making sure to move it at a constant speed so the kinetic energy is not changing. The work that was done to move it there is equal to the change in its kinetic energy. Okay, so for example, let's actually do this. Let's have a hand lift the rock that's 5 kilograms from the ground to 4 meters above the ground. Okay, so it starts down here, and then some person picks this thing up. So some person here picks that up. That's a really long arm, and it does this weird bend there. So maybe I should do it like that. Oh, look how long their arms is compared to their legs there. Okay, so they lift this thing up, and this is the force that the hand is producing on it. We know that's actually a normal force there, and this guy is actually mg, but same idea. So the hand is lifting it up, and it's going at this constant speed, constant velocity, to make it a very simple scenario here. So we pick our system, the rock and the earth, and we'll talk about why the earth is in the system there, and choose a starting in any position from height 0 to height of 4 meters, the beginning to end of our problem. And then we make a free body diagram, which was given right here. I'll move to the next page. Okay, now we plug the work energy, notice not work kinetic energy, but work energy theorem. However, there's a very, very, very important thing to think about. Every type of potential energy has a force associated with it. That should make sense. We know that so far, any amount of change in energy is just some force that's gone through a displacement. So a particular type of energy, potential energy, shouldn't be any different, and it's not. In this case, that force is the gravitational attraction between the Earth and the rock. The Earth pulls the rock down. The mass of the Earth pulls the rock down. We don't want to count the effects of gravity twice. We don't want to count this gravity twice. And that's true for any potential energy. We're talking about gravitational potential energy in this case. So we have one of two options to choose from. Option A, treat gravity as a force that does work, and so we're going to express that in our equation. The sum of the work is equal to the change in kinetic energy plus the change in potential energy. So we can either think about gravity as being a work term on the left side here, so we could think about it as a gravitational work term on the left side, or, and this is a true or statement here, or we could get rid of this and actually move it to the other side here as a gravitational potential energy. Okay? And oftentimes I'd write it, I write the W differently. I write the W instead like this, where I'm showing that I'm crossing off this work term and I'm moving it over to the right side as this gravitational potential term. Okay, so you could do either. One is not better or worse than the other. They're just slightly different from one another. Oftentimes, people will find that gravitational potential energy is usually a little bit easier to think about and calculate. Not always, though. So in this example, we're going to try and find gravitational potential energy. So we're going to use option B in this example right here. Again, make sure that you don't have both a gravitational work and a potential energy of gravity at the same time. And that's true not just with gravity, that's true with anything that you might have a potential energy. Don't have the same force that's doing the work here that's causing some potential energy. Don't have that show up twice there. Otherwise, you'd literally be counting whatever that thing is twice, and that would be terrible. Okay, it would not be accurate. That would be correct. All right, so then if we treat it as a gravitational potential energy, we're not treating it as a work term there. So then I look at my free body diagram, and if you recall, it was just the force from the hand going up and the force from gravity going down. If gravity is showing up here as this gravitational potential energy, the ending potential energy minus the beginning potential energy, then the only force left that's doing work is the force that the hand is doing. And so that's the work that the hand is doing on our rock earth system. Okay, but some of these terms will be zero. Since the rock has moved at a constant speed, the starting and ending kinetic energies must be the same. So it doesn't matter what they are, the ending bit minus the beginning bit, this whole thing is going to be zero. Okay, cool. And so they were going to cancel out. Since we decided to call the ground the position of zero potential energy, that means that this guy is going to be zero as well. So now we have something that's pretty simple, and this is why we chose this scenario here, that the work that the hand is doing on that rock is going to be equal to the gravitational potential energy gain of that rock, and truly the rock Earth system there. So now we plug the equation for work in, where it's F dot delta X, and the way to resolve that dot product there is just the cosine of the angle between those two vectors there. And if I want to write this particularly there, these two are both vectors, so they have little vector hats on top of them. Question, is work a vector? Work, the change in energy, is that a vector? Well, energy, does it have a direction? You can kind of say yes, but it doesn't really. You could say, hey, energy has a direction whether it's going in or out of your system, and I would agree with that. But work itself, could I draw it as a vector in physical space here, that its energy is moving to the right or moving to the left? Not talking about the system, but actually talking about the actual picture of the rock here. And no, you can't. So it doesn't have a direction, so it's actually not a vector, it's a scalar quantity. I do agree that it has a direction in a different context there of in or out of the system. All right, so in this example, since the rock is moving at a constant velocity, the acceleration of the rock must be zero. And the total force on the rock then must also be zero, meaning we have balanced forces up here. Chunk, chunk. The force on the hand must be equal to the force of gravity because of this. So the work that the hand does must be equal to mg, that's the force of gravity, times the angle between the hand and its displacement vector. Let me move this thing down here. Oh gosh, I'm resizing it. Let me move that thing down there. And let's draw the displacement vector in here in a different color. We know that we're moving this thing upwards like this, and I'll keep it as delta x even though it's going in the vertical direction. And you go, hey, what's the angle between this force that the hand puts on there and the delta x? And you go, they're going in the same direction. The angle between them is zero. That's where the zero comes from. And then multiplied by the delta x. Now, we wrote it as h here, and we're going to write it as h in just a little bit here. But it's actually delta x since we're talking about the work term there. Now, you might say, isn't that a height change here? And I would agree with you on that. All right, so more on that in a bit. So then this thing would be like delta x here, and we can put in all of our numbers, since we have all these numbers, we could actually go and calculate that. Now, since this is always, since gravitational potential energy, you know it only depends on mass, gravity, and how high that something is, or really how much you've displaced it up from the surface of the Earth, you might say, or away from the Earth, really. Then a lot of times people will call that a height, but notice that it is actually truly a change in x if you're talking about a change in energy, a work, which is a change in energy. Now in this case, we're actually going to go ahead and we're going to change, and I'm going to change this back to an h here. Why? Well, because I know that work here is a change in energy, and in this case, the change in energy is the change in gravitational potential energy. Okay, cool. So now this is going to get into what's the difference between a change in something and just that something. Well, we said that the change in something is the ending bit minus the beginning bit. So I'm going to write it a little bit differently here. I'm going to put UG as the ending bit and minus UG naught, the beginning bit, the gravitational potential energy at time zero for our system here, for our scenario. And we knew that this was zero in this case. Okay, cool. So that's zero in this case. So you're going from a displacement of 0 all the way up to a displacement of 4. And when you do that, then it's just going to be equal to the ending amount because this beginning bit just happened to be 0. That means that when you go and calculate this, Now, when we go and calculate that, we've already actually simplified this and knew that that was actually 0. So when I go and calculate this, I'm actually finding just the ending amount of my gravitational potential energy. And so then this thing isn't actually a delta x in this case. Instead, the beginning bit was 0, and we already subtracted the beginning bit. So another way to think about that, so it is not a change in gravitational potential energy that we calculated here. We actually just calculated the ending bit. So another way to write this would be mg cosine of 0 degrees and then multiplied by my ending position minus my beginning position, and that would be equal to my ending gravitational potential energy minus my beginning gravitational potential energy. Now, here's what I was just talking about. This guy, we set it to be 0 down there at the bottom. Well, that means that my position at the beginning was 0 as well. And so now when both of those guys are 0, now it's just mg cosine theta times the ending position. Well, the ending position, since it's a height here, most people will then call that ending position, some height that you moved up there. And so then you'd just be calculating the ending gravitational potential energy. So most oftentimes it's written as something like this, but notice that what I'm trying to point out here is that this U is not a change in gravitational potential energy. And if I wanted to write it maybe more accurately or a little bit, maybe a little bit more accurately, we need a little subscript G on this guy because that's the gravitational potential energy. That's not any potential energy, just the gravitational potential energy. To write it slightly more accurately here, we'd write it as the change in gravitational potential energy is equal to mg and now some delta x, or I've seen it written as delta h, some change in height there. I've also seen it written as mg delta y. This would probably be the slightly more generic and useful way. But delta h it makes sense because we've been talking about height since we've been in elementary school, so we usually still thinking about it that way, and that's fine too. But notice the difference between a change in gravitational potential energy versus gravitational potential energy at some one height there. So difference between a change in something and just one thing. Okay, all right, moving on. So besides gravity, there are other forms of potential energy. Notice that in the previous example, I always said gravitational potential energy because there are many, many, many different types of potential energy. Okay. Each force each has a force associated with it. For example, what if I took a proton and an electron and I put them close to each other? Well, clearly the proton would be forced towards the electron and the electron would be forced towards the proton. Notice we're using on-by statements here, that this force on the proton by the electron and this is the force on the electron by the proton. They're both attracted, we already know that. Hey, which force is bigger? Because this proton is 1,800 times more massive than this electron there. Which force is bigger? Well, you might say, well, the mass doesn't make a difference when we're talking about charges here. Great, yeah, you're right. So then the mass doesn't make a difference, so the mass difference doesn't make a difference. So then, think about the charge. Which one of these has more charge? You should say, oh, they have the same amount of charge. Remember those? The elementary amount of charge is 1.602 times 10 to the negative 19th coulombs. And it was just the positive version of that and the negative version of this for each one. We saw that. That's supposed to be a 19 there. We saw that in the previous unit there. So it's the exact same amount of charge on both of them. So which one has a bigger amount of force? And at this point, you should be saying, oh, they're the same. But what if this one, the proton here, what if it was like 10 protons? The accumulation of all 10 protons, which has now 10 times the amount of charge, then which one would be a bigger force? And you're thinking to yourself, man, we talked about questions like this before, and this sounds like Newton's third law going on here, because no matter how much charge I have on either one of these things, or how imbalanced that charge is, I have one object here, A, and one object here, B. And even if it's the accumulation of 10 protons on A there, I could talk about those 10 protons as being one object, like we talked about that rock in the previous example as one object there, even though it's made of many, many, many protons and electrons and neutrons. That if I have A attracting B, B must attract A, and it must be the exact same amount of force, and it is. And we could even go and prove that using Coulomb's law here, that the electrostatic force there, we're going to do that as lowercase e, the electrostatic force there is going to be K Q1, Q2 over R squared, and go, oh yeah, when I go and do the math, it doesn't matter which one is Q1 and Q2 because it's multiplication anyways. So when I go and calculate the force here versus the force there, mathematically it comes out to be exactly the same, and proof that Newton's third law is actually true. All right, so then let's keep moving on. If I was to release these charges, they would attract one another and would accelerate towards one another. They have unbalanced forces. So as they move, they could push on something. Oh, so something else might get in the way and maybe they'd push on it. So they have the ability to do work because of their positions. The further apart the proton and electron are, the more electrical potential energy the system has. If I wanted to give this system more potential energy, I would have to push them further apart. Right? They want to go together, but if I got in the way and I pushed them apart there, then I would separate them more, just like I separated the rock from the earth in the previous example, more and more and more. And the rock had more and more gravitational potential energy. Gravitational potential energy to do what? Well, to fall down, to get faster, to maybe push on something else. Same idea here, right? If I push this electron and proton further and further away from each other, now they could like fall into each other more, just like that rock in the earth. Okay. Note that this means that I would be pushing against the electrical force, the electrostatic attraction that we talked about. The work that I do, so if I put my hand in there and I pushed it, and can't really do that with your hand, but you can imagine, if I got something and I actually pushed that thing away, I would be doing work on that something, and I would be pushing against that electric force or the electrostatic attraction that is there. And this force is what gives the system its electric potential energy. Just like that force of gravity in the previous example was what gave that gravitational potential energy to the rock, depending on its position. If I push the electron away from the proton so that it moves at a constant speed, well, the work that I do provides electric potential energy, but no kinetic energy because I'm moving it at that constant speed. There's no change in kinetic energy would be zero. So notice we're looking at this case, but in context of the previous example there. So to move at a constant speed, my force would have to balance out the electric force. So we see that I would be doing work equal to that done by the electrical force, but in opposite directions. So the work that I would be putting into that system by pulling them apart would be equal to the change in electric potential energy, but the opposite of that. I'd be putting work into it, so that would, I would be transferring my energy to it, and it would be storing that, you might say, as electric potential energy. So, my hand pushing against that thing, I would lose energy, but it would gain electric potential energy, you might say. So then we look at this and we go, okay, cool. If I had this original system as this first one and this first one, this first scenario just right in here, then if I took this -1 and I pushed it away here to a higher height, you might say, think about the last example, further away, so now it could fall into that proton even more. So, I would be doing work on this thing. I would be giving it energy there as I pushed it along there. Notice that the force of attraction there is going opposite of that displacement vector, giving rise to that negative sign that's in there. Okay. So the electric force is the force that holds the molecules together in chemical bonds. Energy is released and absorbed in chemical reactions is actually electric potential energy. That's true. Do you remember this graph from back in chemistry? You had some amount of energy and they just labeled it as energy over here, but really we know that it's electric potential energy now. And we said, hey, as we went from we had reactants here, and then we had the products over here. And what do you remember what there was a name for it when it was in the middle of that transition there? It was called the activated complex, where it's in between those, making the reactants to the products there. Anyways, you don't need to know all of that. I'm just trying to help you remember what this looked like there. And there was some sort of do you remember, I actually wrote that in there already. Do you remember that there was this extra energy that you had from here? And you had to like give the thing this amount of energy so that it could actually go down to the products there. Let's read what I wrote here. Do you remember seeing this in like this one in chemistry class? It's a graph of how the electric potential energy of the molecules changes as the atoms are moved to different positions. You may remember that the position of highest potential energy in the middle of the graph is actually called the activated complex. Typically, where do these charged particles get the energy from? Where do they get the energy from to reach this high potential energy position? We usually let a lot of times heat the reactants and stir them around and such so that their particles are moving more rapidly, thus giving them more kinetic energy, which is transformed into potential energy at that point way up there at the top. At this point you may ask, I'll just say one more thing about that. I didn't know if I had written some on the next page. Here we go. Okay, well, I had to give this some energy, so that was like the activation energy. I believe that was called the activation energy. Activation energy to get that thing going. And then we also have, let me do that in a different color. We also have a difference between this height right here, that amount of energy, and this energy right here. And this change in energy, it goes from here to here. Well, this is the amount of energy that I'm either getting out of that reaction or the amount of energy that I must put in and stays inside that reaction or inside those chemicals, really. In this case, if I go from a high electric potential energy to a low electric potential energy, this is endo or exothermic. Oh, remember that. Remember that exothermic. Exo means out or exterior, like an exoskeleton, which is on an ant. Their skeleton, they don't have bones on the inside. Instead, their shell is hard because they have an exoskeleton. The skeleton is actually the outside bit. And so exothermic means heat, thermic, thermos, talking about heat itself. That heat is going outside of the system, or the chemicals in that case. In this case, we're going from a high electric potential to a low electric potential, and oftentimes that'll come out as heat, and this is an exothermic reaction there. Okay, cool. Moving on. At this point, you may ask, can the work done by any force be turned into potential energy terms? As it turns out, no. We want potential energy to be a property of location. Each position has a particular potential energy. So moving an object between two particular positions has to always equal the same change in potential energy regardless of the path that it has taken. Okay, so this is a path-independent function. Okay, interesting. Only forces that obey the criteria can be used to write potential energy equations. These forces are called conservative forces. Forces for which this is not true, like friction or air resistance, must be treated as work terms in the work energy theorem. Why is it? Why is that true? Why is it that true for friction and air resistance as two examples there? Do we want to do friction or air resistance? Let's take friction. We've talked about that a little bit more. If I took some box here and I slid it on the ground there, and let's say it was going that way, which way is friction going? And you'd say it's going this way. Oh, so it's opposing that slide there. Okay, great. But then let's say that in the next instance, after I slid that over, now it's over here. And now I go, I'm going to go ahead and I'm going to slide it back. So I would put some big force on there and slide it back. And when I slide it back, which way is friction going? Oh, it's going now it's going opposite of what it was before. It's always opposing that motion there. Oh, and so that's why it's not this conservative force here. If we think about gravity in this next example, it's a little bit different. So compare the next example to the frictional force there. So what if I took this box here, and I'm going to start at the top state here in all of these, and then move the box to the bottom state. And now notice that the heights difference is the same in all of these. If I let this box drop down here, it changes some amount of change in height there, which we know the change in gravitational potential energy is mg delta h, we could say. And so then the mass of these boxes we're assuming isn't changing. That's good. And the gravitational potential, the gravitational field strength, well, let's assume it's close to the Earth here, so we're not going from outer space, we're just going up a couple stairs there, down a couple stairs. So the gravitational field strength should be constant. So the only thing that's changing the gravitational potential energy is just the height change there. But if I look at each one of these cases, whether I let it drop down, let it slide down, let it go and take it down some stairs, or I have some complex hill and I make this thing go down here, tell me something about the gravitational potential energy up at the top here at the beginning state versus down here at the end state. And if I said, hey, what if it was 0 down here? And let me just make up some numbers here. What if I said that this was 100 joules up at the top there? Well, which one has the biggest change in gravitational potential energy? Or which one has the smallest change in gravitational potential energy? And you'd say, well, looking at the height change there and what I know about this, the height change is always the same. And if this line, this height here is 100, and this line down here is 0, don't they all have the same change in gravitational potential energy? And I'd say yes. So did it matter which path that these things took to get down there for how their gravitational potential energy changed? No. This gravitational potential energy is path independent. And that's what we're talking about when we underlined that section up there on the top there. It's independent of the path that you take. It just matters about the position itself and only that position. Notice that's different up here from our previous example of kinetic friction there, because the work or the amount of energy that is stored or something like that, it's hard to even say because it's not correct to say, for kinetic friction, it doesn't depend on whether it was here or here in the first state or the second state, because the friction is always going to be going the opposite of the way that it's moving. The difference down here is that gravitational force there is always going the same direction, no matter how I'm moving this thing. Okay, so that's the difference between the conservative forces and the non-conservative forces. Okay. Whew. Okay, great. So summing up, potential energy is energy due to some position. Work can change the kinetic energy, potential energy, or both. Every type of potential energy has a force associated with it, right? That's where all energy comes from. When solving, choose to treat that force as if it's doing work or as a source of potential energy, but not both, okay? That's an easy one to make a mistake on, so careful with that. The work done by conservative force, aka gravitational, electrical, Hooke's law, which we're going to get to next, just depends on the starting and ending positions, but not the path the object took between them. This allows us to write a potential energy formula for that force. Now, last but not least, notice that since this is path independent, if I thought about taking these scenarios here, moving the box down these to the different positions down at the bottom, but in different ways and different paths, if I thought about gravity not as a potential energy, but instead as gravity doing work on this thing, which would be equally correct. Well, let's think about that. In this case, we can see that gravity would pull down and it would go through this displacement. And these two vectors here are going in the exact same direction there. And so it'd just be, the mg times the cosine of theta, which is 0, times that delta h, the height there. Easy, easy. But let's go and let's do that for the next one here. What if I treated this as a work term, not a gravitational potential energy term? Well, now I look at this and I go, okay, great. I'm going to write it as Fg instead. Force of gravity there is like that. But now, wait, hold on. Force of gravity the whole thing isn't doing work on this. Instead, you notice it's got some angle between there. So you might say, oh, we'll do component vectors here. Oh, notice this is why we did component vectors in this weird orientation like this from way back in the day. And you go, oh, it's just that force of gravity times the angle there. Well, the angle here is going to be this angle there. So it's Fg times the sine of theta. Now you might say, oh, isn't the cosine of theta? Well, there's two ways to define that, right? Notice I just did a reference angle there, but you could also define it just like this, and you could do the cosine of that thing. It'll work out the same way. Either way you do it, you go, hey, it's only a portion of the force of gravity. Now I got to multiply it by this displacement vector there. But wait, hold on. If I knew what h was, let's say, this is commonly the h would be given here, and I made up a number here, so I don't want to make up h because I might get it wrong. If g was 10, and I don't even know the mass, so there's going to be there's going to be some height here. Well, if I'm given the height, I might not be given this displacement vector here. It'd be pretty reasonable that it wouldn't be given. Well, now I don't know how long this is. And so I don't know the horizontal, maybe I know the horizontal bit and then I could figure it out, but I don't, that now it becomes a little bit more of a complex situation here. Similarly, let's do it over here. Over here is a little bit better because I go, oh, I got the force of gravity going down here. And in this section here, gravity is going against the displacement vector. These are the displacement vectors here. And so it doesn't do any work there. But then here it does work, great, and there it does work. So I could like add those together and it becomes this situation. That's not so bad. But over here, well, check this out. Yeah, I got gravity going down here. And we do have other forces on all these ones here. But we're just looking at gravity for now. What if, how much gravity does work do, or sorry, how much work does gravity do on this system here? And so if I thought about it as work instead of gravitational potential energy, go, wait, hold on. Well, it goes up a little bit here at some unknown angle, and then it does this curve here. So, well, now it's like changing its angle here as it goes down, and then it changes its angle. It does like a little bump there, and then it changes its angle again. It goes back up to there. Whew. So that sounds like a really, really complex problem. And furthermore, I got to figure out like the displacement along all of these different little angles here, and you could see how this is like a near impossible problem. It's not impossible, but at our stage in the game, this is a near impossible problem to be able to solve for the work that is done on the system by gravity. But that doesn't mean you can't calculate it, because gravity doesn't depend on the gravitational, the work that gravity does on this system doesn't depend on the path that it takes, but it actually just depends on where it started from and where it ended. And that's the beauty of gravitational potential energy. That this gravitational potential energy is super easy to calculate. mg delta h, that's it. And I can figure out the change in gravitational potential energy there. And I don't have to worry about any of these angles, any of these displacements other than just the vertical. And it completely simplifies it. So, in summary, you can hopefully see and appreciate the utility in thinking about certain things as a potential energy, because potential energies, since they don't depend on the path, well, where is that up here? I'm reading up here. So moving an object between two particular positions has to always equal the same change in potential energy regardless of the path that it's taken, because it's not path independent there, you might say. Potential energies are usually way easier to use than the work terms that you could use instead of them. And so that's often that's a reason, it's a reason why oftentimes people, when there is a potential energy associated with some force, they'll use it as the potential energy and not the work term, because it's usually easier to calculate it. Now, we know it's equal to the amount of work, so then you go, oh, well, what if I needed to find out the amount of work that gravity did on this thing? Well, that's equal to the negative amount of work. Why is it negative? Well, let's look back over here. If I sum up the work, we know that's equal to the change in kinetic energy plus the change. Well, actually, let's write it like this. We know that the work is equal to the change in kinetic energy, so this is a work kinetic energy theorem. If I did it for like this first case over here of the rock just falling down, and the rock's just falling down, so I only have this force of gravity on it, so then I would only have this work that gravity is doing on it, and that's equal to the change in kinetic energy. Well, now let's think about this mathematically. If I wanted to take this work term and move it to the other side, how would I do that? I would subtract by the work due to gravity here, and I would put this on the other side here, right? And so now I'd have 0 equal to the change in kinetic energy minus my work due to gravity. But wait, if I put it on the other side, we're not thinking about it as work now. We're thinking about it as gravitational potential energy. Oh, okay. So now notice we just kind of defined something that I glossed over a little bit earlier. And we see that the negative amount of some sort of work is equal to the positive amount of its change in gravitational potential energy. Literally by definition here of we think about this change in gravitational potential energy as a positive value. And the work is negative as it's pulling along well, the work isn't negative, the work is positive, I'm sorry, but then if we move it to the other side. So we can see here that if I transform some sort of work into a gravitational potential energy, the sign flips there because of that, because of our math rules there. Okay, cool. That's it. Have a beautiful day. Thank you for watching.